section 5.3, which, if you've been watching your syllabus, we are a day behind what the syllabus says we're going to do. And this will be the last section in chapter 5 that we do. There's one more section that I really like, because I like probability, but the truth is that once we get through section 5.3, then the stuff that's left over in 5.4 is not critical to what we do the rest of the semester. While it's fun to learn, we don't have to have it, and particularly since we're a day behind, then I won't be doing section 5.4. If we stay a day behind, then our next exam will be a day later than what the syllabus says. Right now, the syllabus says it's on Monday. Has anybody paid attention to this? Monday the 18th, so it sounds like it'll be Wednesday the 20th instead of Monday the 18th. That, again, is tentative at this point, but it's doubtful that I'll be able to catch up a date. So today we will continue the discussion with probabilities. I got through 5.1 and 5.2 last time, but there's a little bit in 5.2 that was left undone, kind of intentionally, and that is the addition rule and the multiplication rule. And the reason that I get to them if I can in that first day, but I usually can't. And the reason that I put those off is because when you get to section 5.3, which is today, then the authors say, oh, but wait, there's another version of each of these, and gives you the new version, and now you got 4 formulas instead of 2, but both of the new versions in 5.3 give you the ones from 5.2 by default. So I know that made no sense, so it will as soon as I finish this discussion. So the addition rule is used for probabilities like that. Okay? The probability of an OR statement. The multiplication rule is used for, any guesses? AND statements. A and B. Okay? So, in section 5.2, he gives you an addition rule and says, this rule works if the sets are disjoint. Well then, now in section 5.3, he says, now if they're not disjoint, here's the new rule. So I'm just going to give you the new rule, and it gives you the other one by default. Same thing with multiplication rule. If the events are independent, then you do one thing. If they're not independent, you do another thing, but it gives you the independent one by default. So, let's start this whole discussion with continuing with the dice experiment that we talked about last time. Remember, I had 2 events. I had even numbers and I had little numbers, right? And we talked about different probabilities with those things. Do you remember what the Venn diagram looked like? If I say this is my E circle and this is my L circle, this is rolling a single die with 6 sides. How many numbers will be inside the E circle? Okay, 3. How many numbers will be inside the L circle? 2 numbers. How many numbers are in both? 1, and that number is the number 2. So I put that in the overlapping part of the 2 circles. And that, we said, is the intersection of the 2 sets. The even numbers that aren't in L are 4 and 6. The little numbers that aren't in E, well, there's only one, and it's L. Right? Now, we did these probabilities, both of these, last time, but I didn't give you any rule for it. So let's do them again just by looking at the Venn diagram. I'm missing on here the 3 and the 5. They are in the sample space, but not in either of the circles. So let's do first the probability of E or L, just from looking at the Venn diagram. What does that mean? It means I take my die, I roll it, and I either get an even number or I get a little number. What's the probability that that happens? 4 out of 6. So we know the answer. Now how did you get 4 out of 6 looking at the Venn diagram?
Because there's 4 numbers total within the 2 circles.
Okay. I just hook the 2 circles together, and there's 4 numbers inside here. That's the union of the 2 sets, right? Now this works great for little trivial problems where you can easily draw a Venn diagram and stick numbers in places or events in places. But if you have a big problem like a sample from a population of, you know, several hundred or several thousand people, and you might not know where all the people fall like that. You can't do a Venn diagram. So you need other rules. So the addition rule goes with OR. So I'm going to take this number 4, 6, I'm going to move it over here so we know what the answer is. The addition rule that he gives in section 5.2 is that. Okay? He says, if the 2 events are disjoint, then you can do an OR just by summing their respective probabilities. So let's do that. Just use the numbers there and see what we get. What's the probability of E? 3 out of 6. There's 3 even numbers out of the 6. What's the probability of a little number? L? 2 out of 6. If I add those 2 together, I get 5 out of 6. Is that the right answer? No. We said it's 4 out of 6, and I didn't write it there. There we go. Why did this not work?
Because 2 is counted in both.
Say that louder.
2 is counted in both groups.
2 is counted in both groups. It's counted in the evens, and it's counted in the little numbers. So it gets double counted. So if something gets double counted, you need to subtract it off once. Right? Okay, well, subtract it off once. The number that got double counted was the number that was in both. And the word both is the same as the word and. It's in the E group and it's in the L group. Right? So what I subtract off is the probability of E and L. So that's 3 out of 6 plus 2 out of 6 minus 1 out of 6. And that does give me the 4 out of 6 that I know is the right answer. That's the addition rule. So let me write it up here as a generic A and B formula. Probability of A plus probability of B minus the probability of A and B. And the minus part is because what's in A gets counted, what's in B gets counted, and then what's in both of them gets double counted, so you subtract it off once. You count it twice, subtract it off once, and you've counted it once. Okay? So that's called the addition rule. Now, how does this, I said by default, if you have disjoint sets, this gives you the same rule that he had in the previous section, which didn't have the minus part. How come it works? What does disjoint mean, by the way? Okay, they're separate. The 2 circles don't overlap, which means there's no intersection. There's no elements that are in both sets. So if they're disjoint, what's this probability? 0. You can't get something that's in A and in B at the same time, so this part's 0. So it defaults to the one from before. So you don't need to remember 2 addition rules. Just remember this one, and then if they do happen to be disjoint, this part will be 0 and you'll be fine. All right? Now, multiplication rule. The multiplication rule in section 2 is this. The probability of A and B is the probability of A times the probability of B. And then they say, but this only works if A and B are independent events. If they're not independent, we have to do something else. We have to change this formula a little bit. Now let's try it in this case. I'm going to replace the A with an E and the B with an L. So this is the probability of E and L. What's the probability of E? 3 out of 6. Probability of L? 2 out of 6. When I multiply 3 out of 6 times 2 out of 6, I get
1.
We get 1? No, if I multiply 3, 6 by 2, 6, I don't get the number 1. I get, no? 6 over 36. You multiply fractions, you multiply the tops, you multiply the bottoms. So I get 6 out of 36, which reduces to 1 out of 6. Is that the right answer? Just look at the Venn diagram. What's the probability of being in both of those circles? 1 out of 6. So it worked. If it works, then that tells you that the two events are, in fact, independent events. Remember what an independent event is? Yeah. The probability of one does not depend on what happened on the other one. Remember drawing the cards without replacement? And we say, well, the second one depends on what happened on the first one. If they don't depend, then they're said to be independent. Okay? So this is a test of independence. If this is true, then A and B are independent. If it's not true, then we've got to modify this second piece, this probability of B. Okay? So I need some board space, and I'm going to leave that Venn diagram up there for a second. Let's make up a whole nother example where I can sample without replacement, and so we get some dependent events. Okay, so let's say I have 6 red balls and 4 white in a bucket. All the probability books say in an urn. These are called ball and urn problems. And that's exactly my reaction. Urn? You mean like cremation? Yuck! I'm not reaching in there. So I say something else, like a can or a bucket. Right? So I got a bucket, right? And it's got 6 red balls and 4 white balls in it. Okay? Now I shake it up, mix it all up, and I have Erin draw a ball out of there, right? What's the probability that she got a red ball on that draw? I'm saying 1 for first draw. What's the probability of that? 6/10. Right? 6 out of 10. Okay? Now I shake it up, and I come over here to Amy, and I have her draw a ball. Okay? She doesn't seem that interested. She didn't even look at it. What's the probability that Amy got a red ball? And that was on the second draw.
5/9.
Is it 5/9?
6/9.
Or is it 6/9? You're right, it's 9ths because she didn't put her ball back, right? She sampled without replacement. But is it 6/9 or is it 5/9?
We don't know if she got a red or a white one, so.
Because it depends on what she got, right? So let's draw a tree diagram. When Erin drew, it could be red or white, right? and it's red with a probability of 6/10, and it's white with a probability of 4/10. Last time we did tree diagrams, but we didn't put probabilities on them. I'm going to do that today. You can put probabilities on the branches of the trees. Okay. Now, I don't know what Erin got because I didn't look at her draw and she didn't tell me. But if it happened to be a red one, then when Amy drew, it could be red or white. And if she got a red one, then what's the probability that Amy also got a red one? 5/9. There's only 5 red ones left out of a total of 9 that are left. What's the probability Amy drew a white ball if Erin drew a red one? 4/9. Now what do you notice about the sum of the probabilities on any set of branches? They add up to 1. They have equal denominators and they add up to 1. So 6/10, 4/10 add up to 1. 5/9, 4/9 adds up to 1. And you'll have problems where you'll have more than 2 branches coming out of a point. Any set of branches that come out of the same point, they have to add up to 1. Because you have to take one of the branches and you can't take 2 of them at the same time. Alright? Now let's suppose that Erin drew a white ball. If she drew a white ball, then Amy could still get a red ball or a white ball. What's the probability she gets a red ball? 6/9. And then if Erin drew a white ball, what's the probability that Amy also drew a white ball? 3/9. Okay? So what's the probability? It's not a P. What's the probability that both draw a red ball? Well, now let's think about this. Both is another way of saying and, right? So I can write this as probability of red on the first draw. Oops, I don't want to close that yet. And red on the second draw. This is my own little notation. R1 means red on first draw. R2 means red on second draw. Okay? And an and, I want you to become like Pavlov's dogs, right? The word or, your mouth should start watering and you should think addition. The word multiplication, your mouth should start watering and you think, what did I say? I meant and. When you say the word and, you should think multiplication, right? So the word or, which I've erased, always goes with this addition rule. The word and always goes with the multiplication rule. So this is going to be equal to probability of red on the first times the probability of red on the second, but those are not independent events. Because whether or not she gets a red on the second draw depends on which branch we're on. Right? So what I have to do is I have to use something called conditional probability. And you're thinking, ooh, conditional. We did this before. Is that what you were thinking? Yeah, it is. And we did do conditional probability, but we did conditional proportions. It's the same thing. Right? In a minute we'll do a problem that uses a contingency table, and then it really is exactly the same as what we did before. But a conditional proportion is the same as a conditional probability. So you read this vertical bar as the word given. Okay? So I'm going to put a little arrow under there. This is given. It is the condition. Okay? So we say R2 conditional upon R1, or more commonly we say R2 given R1. And given R1 means given that R1 occurred. And now I can just multiply those things out. And what is the probability of red on the first draw? 6 out of 10. What's the probability of red on the second draw given red on the first draw? 5/9, and that's up here on this branch of this tree. So that's 5 times 9. Right? Now, where do you see these two numbers in the tree? Along the branches for red, red. Right? Well, that's what we're saying. Go red again. So the multiplication rule comes straight off of tree diagrams. To find the probability of any tree, you multiply the probabilities along the way to get there. So if I want to know red, red, what's the probability of 2 reds? Well, it's 6/10 times 5/9. If I want to know the probability of 2 whites, what is that? 4/10 times 3/9. If I want to know the probability of a red then a white, 6/10 times 4/9. So on. See how easy this is? It's fairly easy if you get it organized in a nice tree diagram. Or some other kind of way of organizing it. We'll do a few other ways. Okay? So if this fraction actually works out nice because I can reduce this kind of in my head. But usually you just take a calculator and multiply it out and get a number, get a decimal. Right? But here I can cancel 6 into 9 and leave 2 and 3. And I can cancel 5, leave a 1 into 10, leave a 2. Then I got 2 over 2. So I'm left with 1/3. So this probability is 0.333. Okay? If I tried to use the multiplication rule without a conditional probability, the way it was given back in 5.2 for events that are independent, what would have happened? Well, I would say probability of red and red would be 4/10 times 4/10. I get the wrong answer. So that's another check for independence. Is the probability of an and equal to the product of the two separate? Right? If it is equal, then they're independent. If it's not equal, then they aren't. Okay? Alright, I think I'm done with that example, so let me erase it. And I still want to come back to this one in a minute, but I need a definition for conditional probability. The probability of B given A, that's read B given A, the way you compute that, or at least one way to compute it, is the probability of A and B divided by the probability of A. Now, if I multiply through by the bottom of this fraction, what do I get? Give you a hint, I erased it to write this. What did I have written down that looks like that if I move that PA over here? That's the multiplication rule, right? So I can take the multiplication rule, divide both sides by PA, and I derive the formula for conditional probability. So those two are just algebraic manipulations. I can also turn the conditioning around. The probability of A given B, what would that be?
Probability of B and A divided by B.
Okay. Probability of B and A divided by the probability of B. You divide by whatever probability you conditioned on. Yeah.
So, just a question, if you have the probability of A and B, can't you also write that as probability of A times the probability of B divided by that A, and then cancel it out, probability of A? Does that not work?
This part you said replace it with probability of A times probability of B?
Yeah, and when you divide it by one of those probabilities, doesn't it just count out, or?
You know, I'm so glad you asked that question right there. It's almost like I paid her to ask that question right there. Remember, this works if and only if what? the two events are independent. If you do this, you're saying they're independent. And then what happens is what she said. Then you have this over P of A. P of A is canceled, and you're left with P of B, right? So that derives for me another check for independence. Right? This is equal to P of B. If they're independent, that's true. So you can check the conditional probability of B. You can check the unconditional probability of B. If they're the same number, they're independent events. So that's another way to check independence. But don't do this. Happens on tests all the time.
Okay.
People will, start writing this out and they'll say, "Man, this is this, therefore I cancel and I got probability of B." No, it's not unless they're independent events. So only if independent. Now what about these two formulas? I've turned the conditioning around. The top here is A and B. The top here is B and A. Are those the same thing? Yes, they are the same thing. The word "and" is community. A. Now when you think of things happening in sequence, you'd say, no, they're not the same thing, because if I get a red on draw 1 and a red on draw 2, can I turn that around and mean the same thing? A red on draw 2 and a red on draw 1? Well, yeah, I guess it means the same. It's just kind of going out of order. But it is the same thing. The "and" doesn't matter. Order doesn't matter. So you could still have A and B in the top of this one. Okay, so that's a definition of conditional probability. Another question?
Okay, so if it was written in a word question, and like on a test, you say, determine the conditional probability of A given B. Would that be A slash B or B slash A?
Of A given B?
Yeah.
It's this one.
Okay.
The given word has to be put in the way you say it.
Okay.
If you say, what's the probability of A given B, then you write it that way, A slash B.
Okay.
Yeah.
Wait, so are you saying that in the part where you said only if independent at the top, you're saying that if they're independent, you cancel those out and you're just left with B?
Right, exactly. If these are independent, then the probability of A and B, by the multiplication rule he gave us in 5.2, is just the product of the two. And then that lets you cancel those out, and you're left with just B, which gives you this. So if they're independent, this will be true, but only if they're independent. So this is actually a check for independence. And you don't have to do that check. I can guarantee you on the exam, I will give you some probabilities, or I'll give you a table or something, and I'll say, are these two events independent? So, well, I need to check. So you either do the "and" way of checking for independence, or you do this conditional way. Either one, and that's what you do. So here we go. What's the probability of E given L? Back to my dice rolling trial here. So what am I asking? What's the probability that it's an even number given it was a little number? Now, think about that for a minute. Okay, she said 1 out of 6. A few people are nodding. Okay, here's how it works. This is conditional probability. See my die? I'm going to roll it. Now I'm going to shake it up, because I don't want to have to go get it. I'm going to shake it up, and then whatever's face up now in my hand, right? And I'm not going to tell you what it is, but I'm going to look. Okay? I'm not going to tell you what it is, but I'm going to tell you it's a little number, which means it's either a 1 or a 2. Knowing that it's a 1 or a 2, what's the probability that it's an even number? 1 out of 2. Right? I can use the information in the conditional part. The thing I've conditioned on, I now know to be true. So I know, well, there's only 2 possibilities. If it's a little number, it's either a 1 or a 2. 1 out of those 2 numbers is an even number. So the probability of even, given that it's little, is 1 out of 2. Intuitively, we can figure that out, and that is correct. Let's do it using this rule. That should be equal to the probability of E and L divided by the probability of
E.
I heard L. E. Yep, it's one of those. Morgan says L.
Oh, yeah, sorry.
Emily says L. It is L. How do you know? You divide by the one you conditioned upon. So the B happens here, it goes in the bottom. The A happens here, it goes in the bottom. So the L happens here, that goes in the bottom. So fill in the pieces. What's the probability of E and L both occurring at the same time? 1 out of 6. What's the probability of of L happening? 2 out of 6. There's 2 numbers in the L circle, so it's 2 out of 6. How do you divide fractions? You invert and multiply, right? So I take 2 6, I flip it upside down, I get 6 over 2. The 6's canceled. I'm left with 1 over 2. The number that we thought we ought to
And
get.
since they're independent, you can't just cross out the 2 L's and give the probability B.
That's true. We decided earlier that E and L were independent because the AND thing worked, right? So if you know they're independent, then you say, well, if they're independent, then conditioning on L doesn't give me any information. It's just going to be the probability of E. And the probability of E is, but that won't always work. If I had, instead of saying little numbers, I said big numbers. So I had a B circle with the numbers 3, 4, 5, and 6 in it, right?
4 and 6 would be in the center.
Then they wouldn't be independent. Yeah, you'd have 4 and 6 in the middle. So, but those have to be independent events. Okay?
Actually, it'd be the same ratio if it was E given B, because it'd be 2 out of 4, and that's 1/2.
Yeah, you're right. Now what about this? What's the probability of a big number given a little number?
0.
0, right? And they'll do that to you sometimes. They'll say, what's the probability of this conditioned on another one? And those two things are complementary events. Well, if one of them happened, you know the other one couldn't have. So that's a probability of 0. Or sometimes there'll be certainties. What's the probability of, yeah, I don't want to make up a number. Okay. Now let's talk about an area where conditional probabilities get used a lot, and that's in medical testing. Okay? Medical testing. The example I'm going to go through here, just so that I have numbers in the book, is about testing the fetus of a pregnant woman for Down syndrome. Right? They have this test that they do for Down syndrome. But to me, it's a little easier to think of in terms of like a cancer or something like that. You do a test for cancer. Right? So, there are only 2 guys in this, 3 guys in this room besides me. Right? So we'll do breast cancer. So guys, sorry, you don't get to participate. Actually, breast cancer does occur in males. It's just extremely rare. Now, what is the test, the diagnostic test for breast cancer? A mammogram, right? Now, if a woman goes in for a mammogram and the radiologist reads the mammogram and says, it looks like you have breast cancer, he's saying the results of the test came back positive. Positive means you have it, negative means you don't, right? Now, just because the results come back positive, does that mean they definitely have breast cancer? No. What would they do next? they would go to a biopsy. The follow-up test, which is a better test, right? The mammogram is only so reliable. If you take the mammogram, it comes out positive, you do the biopsy and it comes out negative, then the mammogram gave you what's called a false positive. In terms of conditional probabilities, what is that? Well, it's the probability that you test positive given that you don't have the disease. So I'll say cancer superscript C. What does the superscript C mean? Complement. So that means not cancer. This probability will not be 0. An ideal test, it would be 0. What's the probability you test positive if you don't have cancer? Well, if that never happened, there were never any false positives, then that probability would be 0. But no tests are that good. So let's go to the one in the book on Down syndrome because I have some numbers to plug in. And they put the data from a sample into a contingency table. And so a lot of probabilities can be computed straight from a contingency table. And both of my black markers are fading, so let me see what else I got in here. I lost my blue marker somewhere along the way. Let's see if this one works any better. Yeah, that one seems fairly new. So in the book, it tells us that there were 48 people here, 6 people here, and 54 people there. So what are these 48 people?
Tested positive and have.
They tested positive and the baby did have Down syndrome. Okay. The bottom row of the table is 1307 and 3921 for a total of 5228. Then if I sum the columns, we get 1355 and 3927. And that gives me a grand total of 5282. Okay? So what's the probability of testing positive and the baby having Down syndrome? Well, the and makes you think multiplication rule, and you can do that. But if you have the data set up in a contingency table, you don't really have to go to all that trouble to use all those formulas. You just pick it off of there. How many people satisfied both of those conditions? 48 out of
52,
the whole grand total. You don't use any other denominator unless you're doing a conditional probability. If it's an unconditional probability with no slack, no vertical bar given, then you're going to use the grand total. So the grand total is 5282. So I have 48 out of 5282. Now give me that as a decimal.
0.009.
0.009.
1.
91 to 4 decimal places?
Yeah.
Okay. Now let's, before I do any conditional probabilities and false positives and stuff, is testing positive and having Down syndrome, are those independent events? Now wait a minute. Everybody who was willing to give an answer nodded yes. Does that make sense? Would the results of a diagnostic test be independent of whether or not you have that disease? Shouldn't. That test would suck, right? I mean, you wouldn't give a test if the results of the test were completely independent of whether you had the disease or not, right? So it makes sense they should be dependent. How do I check? Well, if they are independent, if independent, then this probability should equal what? Remember what you said, Jory? You said,
Yeah, E0.
can I separate those out? Right? It would be the probability of positive times the probability of D. Right? If they're independent, you can break up an and like that. If they're not independent, the second one has to be a conditional probability. Let's see if that works. What's the probability of testing positive? It's about 48. How many people total tested positive?
35
Good. 1355 out of 5282. And then the probability of D. 54 out of 5282. That's a row total. So these are marginal probabilities. They're in the margins of the table. So you either use a row total or a column total. So this one is 54 out of 5282. When you multiply those two together, what do you get as a decimal?
.003.
0.003. Give me one more decimal.
Oh, .0026.
0026. Okay. So are they independent? No. If they were independent, these two numbers should be the same. Right? Since it doesn't work to just break up the and, you don't get the right answer, then they must be dependent. Now, they're never, with real data, they're never going to be exactly equal. They will be with rolling dice and stuff like that. But with real data like this, they're never going to be exactly equal. So you have to make a decision, are they close? And they're not close. They're both really small numbers, but this one is 3 times what this one is. More than 3 times. So you've tripled the probability. So that's pretty different. Okay? So this did not work. So I put a slash through my equal sign. So they are dependent. Okay? Like we would hope. We would want the results of a medical procedure to depend on whether or not you actually had that disease. All right, now let's do probability of a false positive. Tell me what that is using conditional probability. What does that mean? A false positive.
Plus.
Given that you don't have it.
Good. That's a plus sign. You get a positive test given that you don't have Down syndrome. The baby doesn't have Down syndrome. Okay. So go ahead and compute this for me. How do I do that off the table? I was looking to see if they had done this one in the book so I could see what the answer was, but they didn't. What does conditioning on this mean? Excuse me. Anytime you do conditional probability, that means your denominator changed. You could use the formula that we had a minute ago for conditional probabilities. The probability of this and that, which we computed here, divided by the probability of the thing you conditioned on. You'll get the right answer. But when it's organized in a contingency table, you can do it like we did when we did conditional proportions. How many people did not have a baby with Down syndrome? So that goes on the bottom. The thing you condition on goes on the bottom. How many people tested positive out of those 5280 or 5228?
1307.
1307. So there's the answer for that conditional probability. Give me that as a decimal.
0.25.
0.25, give me 3 places.
0.
250?
Well, it's just 0.25.
It's exactly 0.25? Sweet. I'll leave it like that. So what's that saying? That's saying false positive rate is 25%. And that's always what we perceive, is that this test is terrible. It has a 25% false positive rate. But, and I guarantee you, mammograms, breast cancer, it's worse. The false positive rate is much higher than 25%. Which is more serious in breast cancer? A false positive or a false negative?
False negative.
False negative, because what happens if you get a false negative? You think you're fine, you go home, you don't do anything. They don't follow up a negative with a biopsy. They only follow up the positives. So a false negative is much more serious. What's the probability of a false negative here? It doesn't have the same consequences, but probability of a false negative probability of negative given D. You test negative, but the baby did have Down syndrome. Okay, same thing before. Now I'm going to condition on the D, so that goes on the bottom of the fraction. Number that were D was 54. And 6 of them tested positive or negative. What's that? 0.111. So there's an 11% false negative rate with this. Now, I mentioned a minute ago the terms specificity and sensitivity. If you're a nursing student or in a medical field, you will need to learn what those are eventually. They'll teach you. But they are the reverse conditions. Okay? So sensitivity means how sensitive is this test to that disease. So sensitivity of breast cancer is the probability that you actually have it given that you tested positive. It's the other way around. Okay? So you can compute sensitivity and specificity straight off of a contingency table, same as this. Well, I only got about 2 minutes left. I was hoping to have time to go through one of the homework problems and at least get you started on it. But I'm afraid I don't have time to really get into it. So I will quit there. Let's see, this is Wednesday, so you have due tonight is the 5-1 and 5-2 homework set. It's all together in one homework set. And then this 5-3 homework will be due Friday night by midnight. Okay? So we'll see you on Friday.